Okay, here's part two. Now we were asking the question, if we have our position with a function of time of something in simple harmonic motion, what would be its velocity at any other random point? And if you are a Physics 1 student, then I want you to fast forward to a certain part in this video that I will post under this link that I posted this video on, because we are about to do calculus, and AP Physics 1 does not require calculus. However, I know a lot of you are in calculus and you might be curious of how it works because some of you have tried using it. But feel free to skip ahead to the part where we're done doing calculus. But Physics C, you are required to do this, so do not fast forward. So here we go. We are going to try to find out velocity as a function of time given something in simple harmonic motion. Let's start with our equation. So there is our equation for the position as a function of time. And you may remember from the beginning of the year that the velocity of some particle is given by the derivative of that equation that you see up there. And ours is written in terms of y, but x and y are really interchangeable. One just means horizontal, one means vertical. It really doesn't matter, it's just a letter. But the point is you take the derivative of that function with respect to time, and that would give you an equation for velocity. So that's all we got to do. We just got to find out what this derivative is. So our derivative, there are a couple of rules that we have to follow, and I'm sure that you are pros at taking derivatives at this point, but I'll just briefly go through it. 4 centimeters is our constant, so we're going to leave that out in front. And we need to take the derivative of the cosine of the derivative of the stuff inside. So derivative of a trig function, and then times the derivative of what's inside the trig function. So derivative of sine is the negative sign, and the derivative of 8.97t is 8.97. So we have to multiply all those things out and try to simplify. And if you forgot that 8.97 actually does have a form of units, and it's radians per second. So I'm going to clearly write out all of the units that I can here. And we've got 4 times 8.97. And the way that the units will work out is we should get centimeters per second. And that makes sense because what we got here is that the amplitude should be in terms of a velocity. So centimeters per second makes perfect sense. And it is negative. You're probably wondering why it might be negative. So what I did for our position versus time equation, we had a cosine that was like this. We had a positive displacement and then let it go, and then it went down. So the velocity at equilibrium, right there, that has a negative slope. So that means it should have a negative velocity when we actually calculate it. So I'm going to erase this. We could do our algebra. And I apologize for my allergies. If I sound like I'm dead, I'm really not. I just have a stuffy nose. So, okay, I erased it twice. Here we go. Finding the velocity at the equilibrium point, we need to plug in the time it takes to go to the equilibrium point. So plug in 0.175 to that equation above. So blah, 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 we plug it in, there we go. And when we crunch all the numbers out, we are actually going to get, surprise, minus 35. And the reason why is because when you plug in the sine of 8.97 times 0.175 in radians, you're going to get 1. So it's going to be 1 times 35, or negative 35. So our speed at the equilibrium point is the maximum. And this actually makes sense. If you think about the energy that's going on, that when you're at equilibrium, you have no more displacement of the spring. So there is no energy stored in the spring, which means it all got converted into kinetic energy. So all of its kinetic energy, that means it has to be whatever the maximum amount of kinetic energy is possible, so it's the maximum amount of velocity. Now let's answer this question. What's our acceleration at the same point, at the equilibrium point? So there is our equation for velocity as a function of time. And acceleration is just the next derivative. So take the derivative again of that equation. So our derivative of that equation is going to be our constant times the cosine. Derivative of sine is cosine. And then times our 8.7 radians per second again. So then we get this as our equation. So that is a function of, that is acceleration as a function of time. And I'm going to rewrite this in units that are a little more familiar. So in meters per second. And now let's calculate what our acceleration actually is. So plug in that same time again, 0.175. You are going to get a very small number, 0.003. Now that's kind of weird. And if you think about it, it actually should be 0. So here's our graph, or not a graph, our picture. And if we're at the equilibrium point, we have no more force on the spring because the displacement is 0. So looking at our equation here, that x, it has no value. It is 0. So there's no force, which means there is no acceleration. So that actually makes sense. And the reason why I get 0.003 is because every time I made a calculation of a derivative or finding the angular velocity, I had to round because things are in terms of pi, and that is an irrational number. So you have to truncate it or round it eventually. And if you theoretically could take those numbers out to infinity doing your calculations, when we did this calculation for acceleration, we would have gotten exactly 0, but we can't do that. Here's a pendulum again. So we're going to talk about a new equation. So I pull back a pendulum and it swings to the right, comes to a stop, and then it comes right back. And it's going to keep doing that forever. And I want to know a little bit more about that. So how can I change variables to affect the period? If I change the length of the period, you may remember from the beginning of the year that if you make the length of the string longer, then the period will also be longer. But it's not a direct relationship, so it's something kind of strange, and is given by this equation. So 2 pi times the square root of the length of the string divided by g, and that g is the acceleration of gravity. So you can change the period of a pendulum by either changing the planet that you're on or changing the length of the string. So those are our two things that we can change. So the period is proportional to the square root of the length of the string. And for most of our experiments and problems that we're going to think about, we're going to be on Earth. So g is going to remain as 10. With our other example, we have our other most common example with simple harmonic motion is a mass on a spring. So it depends on a couple more things than our pendulum does. It depends on the mass of the object, and it depends on k, the spring constant. That's not kinetic energy, that is the spring constant. So if I have a very, very strong spring, it's going to have a very short period. If I have a very weak spring, so something that's very stretchy, very easy to stretch, it's going to have a very long period. And if we look at how mass is proportional to period, it's just like it was for the pendulum. It's the square root. So increasing the mass will indeed increase the period, but it will not be a direct relationship. And if I increase the spring constant, it will actually shorten the period because it's going to make the spring stronger and have the forces be greater. So the period is proportional to the square root of mass, and it is proportional to the inverse square root of the spring constant. I know that's rather strange, but that's how it is. Think about it as the spring gets stronger, as it has a higher spring constant, it will have a smaller period. Alright, here is our mass on a spring example problem. It's got an amplitude of 3 centimeters, mass of 1 kilogram, and a period of 0.8 seconds. And given that information, let's say we found this experimentally. We set up a mass on a spring and we displaced it 3 centimeters and let it go. And then we timed the period to be 0.8 seconds. We can use all that to find out how strong that spring is. So we just need to solve our equation that we just learned for K. So solve it for K. So I'm going to do a bit of algebra because that is the most inconvenient place in that equation to actually solve because it's in the denominator of a square root. But it's not that bad. So square everything, and we'll have t squared quantity 2 pi squared times m over k. And I'm going to remind you of a trick, or teach you a trick if you're not familiar with it. It's called cross multiplying. So instead of doing this the long way of multiplying by k and then dividing by all the other stuff, just switch t squared and k. You're going to get the exact same result. And it will be this. If you do your algebra correctly, you will have this. So now we just plug in all of our values for the mass and the period. And it will give us a spring constant of 62 newtons per meter. So that's a pretty strong spring. And yes, so 62 newtons per meter. Now let's look at the pendulum and the period and how we can manipulate things. All I am saying is that it has a length of 2 meters, and I set it into motion. You have no idea what the amplitude is. You have no idea what the angle that I pulled it back to, and I yet still ask you what the period is. If you look at the equation, though, you notice really quickly there's nothing in there about the amplitude. It only depends on the length, and it only depends on g. So the angle that you pull it back to, or the height you pull it back to, does not matter. So this is a simple calculation, and then our period ends up being about 2.8 seconds. So let's do a slightly different example where I have 100 kilogram mass instead. So I made the mass much, much bigger. And I still have a length of 2 meters, and I ask you, what is the period? Well, if you're clever, you'll notice it's not any different because our equation does not depend on the mass. So it only depends on the length and g. So here's a different question. What length would you need to have a period of 1 second? Now, why would I want it to do that? If you think about a grandfather clock, a very old school clock, where the time is actually measured by a pendulum swinging inside the clock. And it is calculated that the tick-tocks are half of a period. So really a better question would be for a period of 2 seconds. But let's just do this example to show why you can do this. And if we had that period length is close to 1 second or 2 seconds or some very easy round number, we could very accurately keep track of time. So let's figure out what length we would need to have a period of exactly 1 second. So we need to solve this for the length. So let's solve this for the length. So square both sides, and we get this. And then we need to solve that for L. So divide by 4 pi, and then eventually multiply by g. And then there we go. Now we can plug in everything for length. So more accurately, you would use 9.8. If you wanted to make an actual clock and make it as accurate as possible, we would want to use 9.8. But for this example, we'll use 10. So then we plug in all of this, and our length is about 0.25 meters. So if we had a pendulum of 0.25 meters, as close to that as we could possibly physically make, then we could have something that could very accurately measure time for us, because the period is exactly 1 second, so we can use that to keep track of time. let's do a summary because we've gone through quite a bit. So we have two very common things that we'll see a lot of in simple harmonic motion, and that's the period, and the two things that we'll see it most often for is a pendulum or a spring. So the period of a pendulum is 2 pi times the square root of L over G, and the period of a spring is very, very close to that equation, but instead of L over G, it's M over K, where K is the spring constant and M is the mass. Then we have the position equation. So the position of some particle in simple harmonic motion is given by this equation, where A is the amplitude, and the amplitude means what is the maximum displacement that it can have. So what's the farthest it goes away from equilibrium. And then that times the cosine of omega t. Then, finally, if you were interested in calculus or if you were in physics C, our velocity and acceleration are given by the derivatives of that equation with respect to time. So graphically, here's a reminder of what it looks like. We are looking at things in radians. So at the maximum values and in the middle, we have separations of 2 pi. So from the highest point to equilibrium, we have pi over 2, then it goes to pi, then 3 pi over 2, and then 2 pi. And then the cycle continues to repeat itself. Then we have two equations for force and energy of a spring, and it is given by this. So the force of the spring is minus kx, and then the energy of a spring is 1/2 kx squared. And if you were paying attention to calculus, then you might notice that the derivative of the energy of the spring is the force of the spring, and the integral of the force of the spring will give you the energy of the spring. So if you're interested in calculus, this is another example about how that fits into play. So I apologize for this video being very long, but there's just a lot of information, and this unit starts to summarize a lot of old units together in this topic. So bring your questions to me as you work on some questions and problems in class, and we will tackle everything else from there.